Good morning, good evening, good afternoon, wherever you may be. Today we're going to finally do what no other glober has ever done, and that's to answer the question that the Floats have been asking us for the last 7 years or so. Where's the curvature? No, that's a lie. We've been showing you guys curvature for the best part of a decade, but it's just amusing to seeing the lengths you go to ignore it. And today we're going to show curvature by measuring angles to this huge TV tower in Sydney. All right, so on Sydney's lower North Shore, there are 3 TV towers that send out the free-to-air TV signal. There's this one in Gore Hill down the bottom, this one up here in Willoughby, which was actually dismantled a couple of years ago, but it's still on Google Earth, and this one up here in Artarmon, and that's the one we'll be using for these measurements. First job is to try and get an accurate elevation for the tower. So what I did here is find 2 state survey benchmarks with known elevations, and then use my theodolite to take some vertical angles to the top of the tower, and then do some pretty simple trigonometry to get the elevation. And it's important here that I use 2 benchmarks that were relatively close to the tower so that the effects of refraction and curvature would be so small that we can ignore them. All right, so here are the 2 marks in question. SS 165 660, which is about 250 meters from the tower, and SS 25372, which is about 400 meters away. So here I am with my theodolite set up over the closest benchmark, and if you download the New South Wales Survey Marks app from the App Store, you can see that this mark is 103.48 meters above sea level, and with my theodolite 1.61 meters above that, I get an observer elevation of 105.09 meters. So then I pointed the theodolite up to the edge of the tower and got a reading of 48 degrees, 23 minutes and 49 seconds. But just to average out any error in the instrument and or the setup, I also get a reverse angle where I flip the telescope upside down and spin it around to take another reading. And that was 311 degrees, 36 minutes and 21 seconds. So you subtract that from 360 degrees and we get 48 degrees, 23 minutes and 39 arc seconds. So the average of those 2 is down the bottom here, 48 degrees, 23 minutes and 44 arc seconds. And the plus or minus on those measurements was 5 arc seconds, which is 1 part in 1,000 of 1 degree. So that's the level of accuracy that we're working with here. Also remember that these are zenith angles, so if we want to know the elevation angle, we simply subtract that from 90 and we get 41 degrees and something else. All right, so because we're only a few hundred meters away, then there's hardly any drop from Earth curvature. Well, at least theoretically, hardly any drop. So we're going to model this with a simple right-angled triangle and then use trigonometry to work out how much higher it is than our observer elevation. And if we plug in all the numbers, we get an elevation for the tower of 327.59 meters. But now I'm going to skip ahead a little bit here. So when I took measurements from the second location and used the same trig to work out an elevation for the tower, I was getting an elevation that was about a foot lower. So I knew there was something wrong. And I finally figured it out. What I was doing was actually measuring to the edge of this big disc-shaped thing at the top of the tower, not to the center of the tower. And obviously that edge is closer to me than the center, so I needed to work out the radius of that disc, which is the green bracket here, and then make an adjustment to the distance. So let's do that. On the left here, we've got the view through the scope of the theodolite, and you'll see both vertically and horizontally, we've got these stadia lines. Now these stadia lines are etched into the glass, just like the crosshairs, and they are a precise angular distance apart. And the angle they make is 10 milliradians. And if you flirfs don't know what a radian is by now, probably a good idea to go and look it up. All right, so since we know that this is 10 milliradians, we can scale that against the width of the disk and get an angular width of 4.86 milliradians, which equals 0.2785 degrees. All right, now we need to know what the length of our line of sight is. So we've made a right angle triangle here, just using the original distance and height. and using Pythagoras, we can work out a line of sight distance of 335 meters. All right, so now that we have the distance and the angular size, we can work out an actual size. We simply plug those values into the angular size formula and we can get a diameter for that disc of 1.63 meters and therefore a radius of 0.81 meters. So our measurement distance over the ground is actually 0.81 meters closer than we first thought. So let's do the simple trick again with the correct distance, and we get an elevation of 326.87 meters. Boom! But as I said earlier, I wanted to go to a second benchmark to double check that elevation. So here we are set over that second benchmark and have an observer elevation of 106.61 meters. And here are both the forward and reverse zenith angles taken from that station. And we get an average angle of 61 degrees, 38 minutes and 51 arc seconds. And the variance in those two measurements is plus or minus 3.5 arc seconds, which if you convert that to degrees, it's plus or minus 1,000th of a degree. Again, this is the level of precision and accuracy we're dealing with when using theodolites. It's in the region of thousandths of a degree. All right, so if our zenith angle is 61 something degrees, then our elevation angle is 90 minus that, which is 28 something degrees. We also use an adjusted distance to take into account the diameter of that disc we are measuring to, and we end up with an elevation for the tower of 326.90 meters, which is only 3 centimeters different to our first measurement. Now, the closer benchmark at 250 meters should give a more accurate height than the further benchmark, but that closer benchmark was a Class D benchmark, while the further benchmark was actually a Class B, so it should be a bit more accurate for its elevation. So let's go somewhere in the middle and use an elevation for the tower of 326.89 meters. And we'll say that that's accurate to within about 2 centimeters, which is less than an inch. Right, now what happens when we move further away? So this is where we'll be able to distinguish between whether the Earth is flat or whether it curves away at 8 inches per mile squared. So here I am with my theodolite set up over another benchmark, but this time we're about 5.5 kilometers away from the tower. That's about 3.5 miles in freedom units, and if you do the quick math with 8 inches per mile squared, you'd expect something in the order of about 8 feet of drop. But we are looking through an atmosphere, and that atmosphere will typically bend light downwards and raise the apparent position of the tower by just a little bit. So instead of 8 inches per mile squared, it's actually a little under 7 inches per mile squared, 6.86 inches per mile squared if you're assuming typical atmospheric conditions. If you use metric like a big boy, you'll get an expected drop of 2.05 meters. All right, so let's make a prediction for what that angle alpha, which is the elevation angle to the tower, what it should be if the Earth is flat. So in this first line up the top, we want to work out how much higher the tower is than the observer, and that will become the opposite side of our right triangle, and the adjacent side of the triangle is the distance over the ground, which is that 5.5 kilometers. So take the arc tangent of that to get alpha, and it works out to be 2.79 degrees, and that is our flat Earth prediction. Now for the globe, we do exactly the same thing, but this time we have to account for that 2 meters of drop over the 5.5 kilometers, so we get a slightly lower angle of 2.7689 degrees. Right, so here's all the relevant info. We've got the distance, we've got the observer elevation, the delta height, which is just the difference in elevation between the observer and the tower, and we've got the expected amount of refracted drop. So then on the left, we've got the calculations for the flat Earth, the expected elevation angle of 2.79 degrees, but with my theodolite, we're actually measuring the zenith angle, so we need to subtract that from 90 degrees, and then I've just converted that into degrees, minutes, and seconds. On the right-hand side are the same calculations, except we've taken the 2.05 meters drop into account, so we get a slightly different angle. So flat Earth, 87 degrees, 12 minutes, 36 seconds. And globe, 87 degrees, 13 minutes and 52 seconds. And look what we measured. 87 degrees, 13 minutes and 45 seconds. So up the top here, you can see how that compares to the predictions. So FE was 12 minutes and 36 seconds, and the globe prediction was 13 minutes and 52 seconds. So my measurement, which is the red arrow, was only 7 arc seconds away from the globe prediction. So chalk up a win for the globe. Now, I know you flurfs well enough to know that you're going to claim that these tiny angles are just too small to distinguish. So in case you're wondering what that 2.05 meters of drop looks like, remember earlier we saw that the distance between the stadia marks are 10 milliradians, or 0.573 degrees apart. And at a distance of 5.5 kilometers, that height of 2.05 meters has an angular size of 0.02 degrees. So if I scale that up against the photo, that red line shows you where the tower should appear through the scope if the Earth is flat. All right, here's measurement number 2, which is actually an Aboriginal engraving site, which is kind of cool. The observer elevation here is 126.81 meters, and the distance is about 6.5 kilometers, which is a little further than measurement number 1, so we'd expect a little more drop. Feel free to plug the distance into the Metabunk curve calculator by yourself, but at this distance we're looking for a refracted drop of 2.83 meters. So here are all the numbers again. On the left we've got the flat Earth, and we do the trig without the drop and get a predicted zenith angle of 88 degrees, 14 minutes and 4 seconds. On the right we incorporate the drop and we get a prediction of 88 degrees, 15 minutes, 34 seconds for the globe. All right, so 14 minutes for FE and 15.5 minutes for the globe. And what do you know? Not surprisingly, we're around that 15.5 minutes mark, which matches the globe, obviously. In fact, the forward face measurement was almost spot on. But once you take the average of forward and reverse, I was a few arc seconds off. So again, at the top here, you can see the 2 predictions. 14 minutes and 4 arc seconds is the FE prediction, and 15 minutes and 34 seconds is the globe prediction. And then you can see how close my measurement was to the globe prediction. All right, measurement number 3, and this one was a little over 10 k's away from the tower, and according to Metabunk, the drop on this one should be about 7.35 meters. Problem was that when I arrived, there was a little boat parked right up on the curb, and I couldn't actually set up the theodolite over the benchmark. So I had to set up a few meters away, but because the ground sloped away a little bit, I had to improvise to get an accurate observer elevation. So here's what I did. I measured that distance along the ground between the benchmark and my theodolite, also measured the height of the instrument at that point, and then measured an angle down to the benchmark itself. And with those 3 values, I could plug them into a triangle calculator and get an adjusted height of 1.43 meters, which when added to the benchmark of 73.05 gives me an observer elevation of 74.48. All right, so here's all the calculations again. On the left is FE, and we're expecting an angle of 88 degrees, 37 minutes and 0 arc seconds. On the right, we have the globe prediction, taking into account the 7.35 meters of refracted drop, and we get 88 degrees, 39 minutes, 25 arc seconds. So that's almost 2.5 arc minutes of difference between the 2 predictions, and that's about 4/100ths of a degree. And remember, we're measuring in the range of thousandths of a degree. And absolutely no surprise to anyone, but again, the measurements were within a few arc seconds of the globe prediction. So remember, FE prediction, 37 minutes, 0 arc seconds. Globe prediction, 39 minutes, 25 arc seconds. Yeah, and the measurement was at 28 arc seconds. And again, here's what 7.35 meters looks like through the scope. So you can see here that the difference between a flat Earth and a globe is easily distinguishable with this kind of equipment. All right, so let's recap what results we had. The predictions for measurement number 1, so the difference between the globe prediction and the FE prediction was 76 arc seconds. My measurement was only 7 arc seconds away from the globe prediction. The predictions for the measurement number 2 differed by 90 arc seconds, and my measurement was only 4 arc seconds away from the globe prediction. And for the third one, the difference was 145 arc seconds, and my measurement was only 3 arc seconds away from the globe prediction. All right, we're at the end, and obviously I have some questions for the flurfs. Number 1, are these measurements consistent with Earth curvature? And this is basically an intellectual honesty test. So I made predictions for both flat Earth and the globe, and the measurements were really close to what they should be if the Earth was a globe. So the answer to this one is a clear yes. Question 2 though, are these measurements consistent with a flat Earth? So again, I made some predictions for what the angle should be on a flat Earth, and the measurements were nowhere near those predictions. So flurfs have a few options here. Maybe you could say that you don't have a model, and that's fine. It just means that your answer to question 2 has to be an I don't know. And then we're just left with the conclusion that the globe model is the only model that makes accurate predictions about reality. Or your second option is that you could say that you disagree with my predictions for flat Earth. Maybe they didn't include some bullshit of yours that you think I didn't take into account. Well, congratulations. It's now up to you to take your particular bullshit into account into your prediction. And I don't care what your particular bullshit is. Maybe you think I should take the diffraction limit into account somehow. Maybe it's hashtag shit shrinks. But whatever it is, my standard response will be something along the lines of, I have made the correct calculations. If you think they are wrong, then you need to provide the correct calculations. And if you can't provide the correct calculations, then clearly you have no idea how your particular bullshit affects the calculations, and you're just throwing out buzzwords. Or the third option is to simply accept all these predictions as valid and therefore conclude that the globe model explains reality better than a flat Earth model. All right, that's all for this one. See you all again in 6 months.